Hello, hello, hello. Welcome back, guys. It is Friday, the 7th of August, and today we're going to do some of that chemistry for the ESAT. Ooh, managed to get one like already without any viewers. Love that. Oh, so yeah, today, chemistry day. So I've done so much of the math one, the math two, the physics, really focusing on those physics and engineering applicants. But I've had a few people come in the comment section and in the Discord server requesting a bit of work on the chemistry. And so I thought today I'd just sort of bookmark some time. That's not the phrase, whatever the phrase is. Like clear some time and just sort of go through the chemistry. So I think I'm going to go through the spec. I might do, because I've never done a live solve of any of the previous ESAT stuff. So I haven't got the paper. Actually, no, I obviously will have the papers downloaded from when I did them last time. But I might go through those. We'll see. I probably did them from websites. It'll be fine. We'll get some papers. We'll solve them. Just to give a sense of how exam technique looks like for the chemistry side of things, just so that you guys don't feel sort of left behind or left out. So without further ado, let's just kind of jump straight into it. So hold on. Wait, I say straight into it. You guys are going there. We're going to have the guide here. There we go. So getting into what the chemistry has in store for us. We've got, all right, we'll start off simple. So structure of an atom. Obviously, you've got a central positive nucleus where all the mass is. It's got protons and neutrons, and you have electrons in shells moving around that. So relative masses and charges of the protons, neutrons, and electrons. Neutrons, mass 1, charge +1. Neutrons, mass 1, charge 0. Electrons, mass functionally 0, charge -1. So when you're considering the mass of a nucleus, mass of an atom, you're really just considering the mass of the nucleus. And so that is all kind of stuff that you did in GCSE and maybe a bit in the early stages of A-level to do with the sort of, masses of atoms. So know and be able to use the terms atomic number and mass number. So in this case, the mass number is the number at the top, and the atomic number is the smaller number at the bottom. The atomic number telling you the number of protons, the mass number telling you the combined number of protons and neutrons. So if you're working out the number of neutrons, you just subtract the two. I imagine all of this is fairly standard for a lot of you. Still worth saying just in case. For any atom or ion. So for an atom, there's equal numbers of protons and electrons. And for ions, you work out how many electrons need to be gained or lost relative to the number of protons in order to give the ion of the correct charge. So you have to be able to use the atomic number to write the electronic configurations for the first 20. So that's the GCSE format, really. So up to 2882, where there's a maximum of 2 in the first shell, a maximum of 8 in the second shell, maximum of 8 in the third shell, maximum of 2 in the fourth within this model. You have to know that the number of electrons in the outer shell is given by the group in the periodic table, and the number of occupied shells is given by the period or the row of the periodic table. So in this case, this is potassium. This is in period 4, group 1, which means we're filling up to the 4th shell, and there's 1 in the outer shell, which is how that works. So definition of an isotope: same number of protons, different number of neutrons. So they have different mass numbers. Using data to identify the number and abundances of different isotopes. Let me go over into the guide just to see exactly what they want you to do for that. If they have an example, maybe I can use to demonstrate. So what was this? This is 1.5. Here we go. So abundances. So isotopes obviously vary by the number of neutrons that they have. And here, okay, so this is what they're talking about. So the abundances can be used finding the mass spec reading. So they're ionized accelerated. What they do is they give you sort of peak. So relative abundance, well, that can't be correct. You can't have a relative abundance of 100. It may have arbitrary units or might show relative abundance. If relative abundance is shown, the MZ peak caused by the most abundant ion is given a value of 100, and all other peaks are given relative to that. Got it. So relative to the 20, there's about sort of like, I'd call that about 13% on 22, and maybe about 3% on 21. And this would give you the relative abundance of these isotopes of neon. So for boron, this is telling us that about a quarter of it. So if I were looking at this, what I would see is if I have sort of boron 11, so the boron 10 to, that's not how you write that. Boron 10 to boron 11, it looks to be, boron 11 it looks to be in a 1-to-4 ratio, basically. So 20% of it is boron 10, 80% of it is boron 11, and I would expect that to therefore give us a relative mass of 10.8. Or here they've given us the relative number of atoms, where again, they've given us that sort of that 1-to-4 ratio a bit more explicitly, which again would allow you to get that 10.8 relative atomic mass. And reading ahead, yep, that's exactly what they did. Okay. So for 1.6, no one used the concepts of relative atomic mass, including calculating values from given data, like I just did. So in this case, if 80% is, you can either say 80% of it is 11 and 20% of it is 10 divided by 100%. Or you can just say 80% is 0.8 times 11 and 0.2 times 10. Now, you could go ahead and calculate that as being 8.8 plus 2 is 10.8. Or alternatively, if you're good at this, you can use this concept of a number line, where it's going to vary, we know here, linearly between 10 and 11, and it is going to be 4/5 of the way towards the 11, because there's 4 times as much 11 as there is 10, which means it's going to get to 10.8. So that's kind of another way you can think about this. Alrighty then, going into the periodic table. We have already got ahead of this curve. So the periods are the rows, which tell you the number of occupied electron shells. The groups are the vertical columns, which tell you the number of electrons in the outer shell. So they're ordered in increasing atomic number. We know this. So metals are towards the left. So alkali metals are in group 1. Alkali earth metals are in group 2. Most common nonmetals in group 16. Those are oxygen and sulfur. The halogens, so fluorine, chlorine, bromine, iodine. Noble gases, can't be bothered to learn those. Transition metals in the middle. No one used the relationship between the position of an atom and the electron configuration we've talked about. Understand that elements in the same group have the similar chemical properties, specifically because, by the way, they have the same number of electrons in the outer shell. Down a metal group, reactivity increases down. Reactivity increases down a metal group and up a non-metal group. Let's also talk about why. So you have to think about what metals and non-metals are doing in order to gain a full outer shell. Because in chemistry, the motivation behind any atom of any element is to gain a full outer shell. If you are a metal, you gain your full outer shell by losing your outer electron. So anything that makes it easier to lose an electron makes it easier to react. As you have your outer electron in further electron shells from the nucleus, the most dominant effect here is that the charge is just further away from the positive charge in the middle. And given the electrostatic force of attraction goes as 1 over r squared, that means there is less attraction and that electron is more easily lost. The reverse is true for nonmetals, which have to gain electrons. So if there's like a hole here, and we need an electron to fill that gap, anything that makes it easier to gain an electron is going to make you more reactive. So that is when you have smaller atomic radius, when the electron shell that you're filling is closer to the nucleus, so there is stronger attraction and it is easier to gain that electron, and so therefore it's more reactive. So always thinking in chemistry, like follow the electrons. Golden rule in chemistry, follow the electrons. Here, this completely explains these reactivity trends that are given. So C3.1, understand that in a chemical reaction, new substances are formed by the rearrangements of atoms and their electrons, but no nuclei are destroyed or created. That tracks. So it's done by electrons. Nuclei untouched, electrons transfer or get shared or something like that. Atoms get rearranged, but the nuclei themselves stay exactly as they are. So if there are 12 carbon atoms before, there will be 12 carbon atoms after. 3.2, know the chemical formula for simple, common, ionic, and covalent compounds. So I'm thinking about knowing, for instance, your nitrate ion, your sulfate ion, your carbonate ion, your ammonium ion. Your covalent compounds, you might be thinking, CO2, O2, N2, all of your halogens. For instance, methane, I would put in there. Ethane, sort of your simple organic molecules, I think you should definitely know. And the rest of it, I think, yeah, we'll see that how we go. So solids, liquids, gas, aqueous, I think you're familiar with. Construct and balance a chemical equation, including ionic and half equations. Let me see if there are any examples I can use to demo this. So that was 3.4. Where's 3.4? 3.1.4. Got it. Right. So, boo, give me an example. Boo, give me an example. No. Okay. So let me kind of demo these in case you need this. Balanced equation for the reaction of sodium. How does sodium exist as sodium? How does oxygen exist as O2? To form sodium oxide. This ionic compound, what ions are present? Sodium forms Na+, oxygen forms O2-. In order to balance these charges, sodium oxide must be Na2O. There must be 2 sodiums for every oxygen. Now, to balance this, to balance the oxygens, we need a 2 to go here. To balance the sodiums, we need a 4 to go there. Done. Ionic equation for the precipitation of silver iodide when silver nitrate solution is mixed with sodium. So we have sodium. We have Na+ present. We have iodine present. Sorry, iodide. I apologize. We're mixing that with silver plus, and it's a solution. Now I'm writing all of this out in full because we're then going to get rid of the spectator ions. So we know it's going to form solid silver iodide. So realistic, and it's also going to then form sodium nitrate, but these are also just going to be aqueous, right? And so what we're going to have is these guys cancel on both sides, and it's really just this silver ion reacting with the iodide ion to form the precipitate. That is the ionic equation that they're looking for. Exercise 17, write half equations for the electrolysis of molten sodium chloride. So what is the sodium doing? The sodium, Na+, is picking up an electron and it's forming solid sodium. What is also happening is the chloride ions are giving up electrons to form chlorine gas, and they're giving up electrons, and we need 2 chlorides in order to balance that. So those are your individual half equations. By the way, while we're here, if you wanted to get the overall equation, follow the electrons. In order to balance the electrons, we need to double this thing at the top while we're here. And then you can simply add these together. So 2Na plus 2Cl minus plus 2 electrons goes to Cl2 plus 2Na plus the 2 electrons, which cancel. And so it's really just 2NaCl breaking down into 2Na plus Cl2, which we expect from the overall equation. Okay. So hopefully that gives a bit of a sense of how to balance, but hopefully as well, that is not new to you if you're going to be doing chemistry for the ESAT. Understand that often chemical reactions can be reversible and do not go to completion. All of the reactants do not fully turn into the products, but the reaction reaches a state of equilibrium in a closed system. We know this. Know the factors that can affect the position of equilibrium. Okay. So what happens here? Increasing the temperature favors, by Le Chatelier's principle, increasing the temperature favors the endothermic reaction so it can mop up that excess temperature. So increasing the temperature favors the endothermic direction, whichever that happens to be in a given equation. Decreasing the temperature favors the exothermic reaction. I spoke about this once. This is a very good interview question, is why Le Chatelier's principle works. I'm not going to go through it here for the purposes of ESAT, but it is really interesting if you want to sit down and get that done. What else do we have? We have something like, for instance, if you have an equation involving gases, if you increase the gas pressure, it favors the side with fewer moles of gas, because that will sort of relieve that increased pressure. If you decrease the pressure, it will favor the side of the equation with more moles of gas, because that will sort of bring that pressure back. It sort of tries to keep itself balanced. You try and do something, it tries to oppose you. Overall pressure. So concentration of reactants and products. Okay, so as well, let's talk about that. So if we have sort of like A plus B going to C plus D, if we increase the concentration of A, that shouldn't be that simple. That, given that we're talking about equilibrium, should be a nice two-way equilibrium arrow. So what happens if we increase the concentration of A? That is going to shift the equilibrium position to the right in order to mop up some of that excess A and turn it into C plus D. Okay. So quantitative chemistry. Use AR values to calculate the relative molar mass. That's not bad. So it's just that I think you're very used to from classroom. Know that Avogadro's number gives the number of particles in 1 mole. Yes. Know that 1 mole, so that's what the molar mass gives you. It's the mass of 1 mole in grams. We know this. Perform conversions of grams to moles and vice versa. Not that bad. I do not enjoy working in tons. A ton is 10 to the 6 grams. Kilograms is 10 to the 3 grams. Whenever you're working in chemistry, you should be working in grams, as opposed to physics, where you're always working in kilograms. Know that the empirical formula is the simplest integer ratio of atoms in a compound. Find the empirical formula of a compound from a variety of data. Percentage composition. I want to do some of these, right? I think this will have some pretty good questions in it. In fact, yeah, let me just go through this. I think this will be helpful. So here, this the Haber process for producing ammonia. Explain how the amount of ammonia present is affected by an increase in temperature. Well, if you increase the temperature, you favor the endothermic direction. Because the forward direction is exothermic, it means the reverse direction is the endothermic direction that gets favored, and the position of equilibrium moves to the left. If we increase the pressure, we favor the side with fewer moles of gas. That is the right-hand side, which has 2 moles of gas. For the left-hand side's 4. So the 1 plus 3 there. Because the right-hand side has the fewer moles of gas, increasing the pressure will move it to the right. So here, if we increase the temperature here, if the forward reaction is endothermic, increasing the temperature will move it in that forward direction because that's endothermic. If we increase the pressure, again, we favor the side with fewer moles of gas, in this case, the left, which has 2 moles of gas for the right-hand side's 4. This one, if water is added to the equilibrium mixture, that is increasing the concentration here, we would expect the position of equilibrium to shift to the left-hand side to remove some of that excess water and turn it into this stuff. So we would expect it to become more pink. The reason why being that if we increase the concentration of water, suddenly the rate of the reverse reaction is now more than the rate of the forward reaction. And so that leads to a sort of net reaction to the left, which will move it to the left. Oh, I didn't realize they had a whole bunch of questions. Yep. Okay. So as I said, so quantitative chemistry now. So a balloon contains 0.2 moles of helium. How many atoms of helium are contained in that balloon? It would be 0.2 times this guy. The end. Because 1 mole contains this much, so 0.2 moles is just the Avogadro's number times 0.2. Calculate the relative molar mass of these guys. O2 is just going to be 32.0. It's that times 2. C6H12O6. Please don't make me do this non-calc. Well, I'm going to say that's 6 lots of 12 plus 2 lots of hydrogen plus 1 lot of oxygen. So 14, 30, 180. Cool. Barium nitrate. So we have NO3 is 64. Add a 14 onto that, you get 78. Multiply that by 2, and it's 160, so 156. And then we add on the barium, and we get 293. Let me just double check that with the calculator. So 137 plus 2 lots of 14 plus 3 lots of 16. No. Why did I get that wrong? So 3 lots, because that I did 4 lots. No, I did 4 lots of oxygen. Guys, chat, why didn't you stop me? All right, so 3 lots of oxygen. No, that is 48. Lies and deceit. Hold on a minute. I'm getting suspicious. Hold on. Times 3 is the 48. No, so it's 48, not 64. Sorry for being an idiot. This is what happens when you don't read questions, guys. All right. This is also why you check your work if you can. So 14 plus the 48 is actually going to get me to 62. Double that up for 124. Add on the 137. We're going to get 261, as I got before. Okay. What's the mass of 0. Well, that depends entirely on what the molar mass of magnesium is, which I'm not given. Well, I suppose in the real thing, I would be given a periodic table, but you would take the molar mass of magnesium and multiply it by 0.01. This is ESAT. They're keeping it not too bad. How many moles of aluminum? Yes. Haha. I shall not apologize. How many moles of aluminum is formed if 5.4 tons are produced? So 5.4 tons, that's 5.4 times 10 to the 6 grams. So it's mass over molar mass. A good time to, so that's 54 times 10 to the 5. What was that? Oh, that was me bringing out my American accent and saying aluminum instead of aluminium. And I'm very, very trained to get into a fight with students after that. So I'm like, do you know what? Bring it. You can't stop me. Right. So 54 and then 27. So that's going to make that 1 and 2. So it's 2 times 10 to the 5 moles. Hey, all I'm saying, if this was a sort of normal tutoring session, you would be finding this very funny. Like the play fighting, it's part of it, right? Okay. So what's the mass in kilograms of 100 moles of sodium hydroxide? Let's get the MR. So 23 plus a 16 plus a 1, 1740. 100 moles would be 4,000 grams, which is 4 kilograms. Okay, nice and fine. Percentage composition, empirical formulas, let's just find out what they mean. So what's the percentage by mass of carbon in glucose? Well, the total mass, like we kind of said before, it's 6 lots of 12 plus 2 plus 16, which I think simplifies the math a lot. So 14, 16 makes 30 times that is 180. Now, out of that 180, 72, so say we had 1 mole of this stuff, right? It would be 180 grams, 72 grams of which would be carbon. And you multiply by 180, and that gives you the percentage by mass. So immediately I'm going to cancel this 10, 9, and 30, 60. I thought it did. So that becomes 4, and it's 40%. Percentage by mass of water in crystals of this. So there are 9 of those. So 10 would be 180. So it's 162 out of the 240 times 100, which looks deeply unfun, and I don't appreciate it. So it would be 81 over 12 times 10, making that 6 and 5, making that something I can't be bothered to calculate. That should really be non-calc if we're doing this for ESAT prep. Right, so for beryllium and oxygen, if we had 100 grams of this, then 36 grams would be beryllium and 64 grams would be oxygen. We convert those to moles. So 36 grams of beryllium is 4 moles, and 64 grams of oxygen is 4 moles. Therefore, the simplest ratio is 1 to 1, and it's just beryllium oxide. And you can apparently also find it from reacting masses. So what is the empirical? Not to be the one. These are exactly the same question. So there's that. So we have now. Okay, so here's how to do one of these. If you have an empirical formula, you know what an empirical formula is. We can work out what the mass of that thing by itself would be. It would be 12 plus 1 plus 32. Which would be 44, 45. Now, in practice, the MR is actually 90, so no surprises. We're going to multiply this thing by 2. And this is the molecular formula. So this thing, use balanced chemical equations to calculate the masses of reactants and products, including there's a limiting. So this is using your mole calculations. In general, the theme is to work out the number of moles of the thing you're given. Use the equation to work out the ratio, and therefore work out the number of moles of the thing you want, and then work backwards to work out its mass or something like that. Working in moles as well for solutions and for gases. So here, what's the maximum mass of magnesium oxide that can be formed from this? So first thing we always need is a complete equation. So magnesium exists as Mg, oxygen is O2. I know that in magnesium oxide, Mg is 2 plus, O is 2 minus. Those are balanced when we have 1 magnesium plus for every 1 magnesium 2 plus for every 1 O2 minus. So in order to balance this, we need 2 on there and 2 on there. So if we have 0.12 grams of magnesium, the number of moles is 0.12 over 24, which would be that over 2400. Cancels for 2. Should not have done it that way, but it's basically it's 0. It's okay. Let me instead say that is 120 times 10 to the minus 3 all over 24. Then that becomes 5 times 10 to the minus 3 moles of magnesium. What is the maximum mass of magnesium oxide? We can see the magnesium to the magnesium oxide is a 2-to-2 ratio, therefore a 1-to-1 ratio. Therefore, there are also 5 times 10 to the minus 3 moles of this. So we need to multiply the number of moles by the molar mass, which is 40. So that's going to be 200 times 10 to the minus 3, which is 0.2 grams. It was stated that the oxygen was in excess. Okay, so in this case, we actually don't know which of these is going to be in excess. We are given the equation, though. So what we're going to have to do is to work out which of them is in excess based on the numbers we're given. So this many kilograms, I'm just going to be lazy here and work in kilograms. So I'm going to say 11.2 over calcium, which is 40. No. Okay, so it does want to divide. So let's divide by 4. We're going to get 2.8 over 10 is 0.28. So it would really be 280 moles because it should have been that times 1,000. But all right, fine. I'll do it properly. Sue me. Oh, no. It wasn't calcium. I haven't read the question. It was calcium oxide. I am chat. Hold me to a higher standard than that. So, okay, fine. The number of moles here is going to be 1120, 0, all over calcium oxide. Calcium oxide is going to be 56. Let's divide top and bottom by 4. Is that going to be something obscene? It is going to be something obscene, and I'm not going to want to work with it. That becomes 2. That becomes 8. Then we get a 0, 0. Oh, no, it's not too bad. 200 moles. Love. So there's 200 moles of calcium oxide. And 11200 over the carbon, which is 12. Yeah, nice spot. I did not spot that. Casually knowing your 56 times tables. That's exactly how to do well in an ESAT. Saves you all those valuable seconds. So in this case, we're going to divide by 4 again. 2800 all over 3. Which I'm just going to leave like that because that does not divide. But I can see that if I'm... So, in other words, if there's that, though... Why am I suspicious? I shouldn't be suspicious. No, we're fine. Okay, so we can see that if there were this many moles of calcium, or rather, let's how do I phrase this? So okay, so because the calcium oxide and the carbon is in a 1-to-3 ratio, it means this thing we would need to divide by 3 to get to the number of moles of calcium oxide we would need to react completely with that amount of carbon. If we divide that by 3, we get a number that's bigger than the 200 available moles we have. Or alternatively, we can say that 200 moles of calcium will react with 600 moles of carbon, which is less than we have. So in other words, the calcium oxide is limiting, the carbon is in excess. So we're going to have 200 moles of this. We want the calcium carbide. It's in a 1-to-1 ratio, so we'll have 200 moles of that, the calcium carbide. And to work out the mass of the calcium carbide, you would do the 200 times the molar mass of the calcium carbide, which is 40 plus 24, which is 64, which is 12800 grams, or 12.8 kilograms. Cool. What's happening here? What's the minimum volume of oxygen that's required to ensure complete combustion of 1 decimeter cubed octane? Now, because the number of moles is just V over 24 if you're working in decimeters cubed, or 1 over 24,000 if you're working in centimeters cubed, we can just, because it's just a scale factor, we can basically use volume as an equivalent measure for moles. So if we have 1 decimeter cubed of octane, what's the minimum volume of oxygen? Well, let's look at this ratio. The mole ratio is 2 to 25. So the volume ratio should be 2 to 25. So it's going to be divide by 2. So divide by 2 here, you get 12.5 decimeters cubed. And that is the minimum volume of oxygen needed to ensure complete combustion. Here, calculate the mass of ammonium chloride required to produce this volume of ammonia, temperature and pressure. This time we actually do need to calculate the number of moles. So 1.2 over 24 is 12 times 10 to the minus 1 over 24 cancels 2. So it's 1 over 20, it's 0.05 moles of ammonia. And we want to calculate the mass of ammonium chloride required. Well, we can see that's a 2 to 2, so a 1 to 1 ratio. So therefore also 0.05 moles of that. And the mass would be 0.05 times 14 plus 4 plus 35.5. You're killing me here. You're killing me. So 0.05 times 18, 53.5. Oh, why are you doing this to me? Like, I'm a good person. I don't deserve this. I don't want to have to. Let's take a 2 from here and put it into here. Times 1.07. So it's going to be 2.5 plus 0. It's going to be the one I would just pick the multiple choice that's closest to 2.5 at this point. Like, this is just, it's just, there's no payoff to that. Like, it's not fun. I don't want to. No, sorry, discipline. So 4 lots of that. Uh, 2.57. Well, 4 of them would be 10. So it would be 17.5. But then we add a couple more zeros. So 0.175. So it's 2.675. Can you just divide 53.5 by 20? I mean, who wants to divide 50? Well, I suppose, yeah. I suppose if you wanted to do the bus stop method or some sort of long division, because that would be the same as 5.35 divided by 2. I suppose it wouldn't be too bad. 2, 4 leaves 1, 6. Yeah, you're right. That is better. 2.675. Okay. Thank you. See, this is why chat keeps me honest. when it's 5 p.m. on a Friday and I simply cannot be bothered to deal with that level of arithmetic. So what's the volume of hydrogen obtained when that much zinc? So zinc is reacting with an excess of dilute sulfuric acid at room temperature and pressure. Well, also, okay, let's talk about your neutralization reactions. Acid plus metal goes to salt plus hydrogen. Acid plus space goes to salt plus water. Acid plus carbonate goes to salt plus water plus carbon dioxide. So here, acid plus metal goes to salt, zinc 2 plus, SO4 2 minus, and hydrogen. So we have 3.25 grams over the 65. Let's multiply top and bottom by 2 here, actually. So that's 6.5 over 130. Well, that looks nice. because that's going to be 1 over 20. So 0.05 moles again. So we have 0.05 moles of the zinc reacting, and therefore we'd have 0.05 moles of hydrogen, and 1 mole is that. So it becomes 24 over 20, or 6 over 5 is 1.2 decimeters cubed of hydrogen. Balancing. So we have 100 centimeters cubed of gaseous alkane. Well, so the number of moles there is 100 over 24,000. Cancels. Is a number I can't be bothered to work out. Oh no, this is all gas, so I cannot do that. Let's just work with reacting volumes because we're dealing in gases. Required for complete combustion. That means the volume ratio is 1 to 4 in gases, which means the mole ratio is 1 to 1 to 5. So it's alkane plus 5 oxygens for complete combustion. Huh. So I'm going to call that CnH2n plus 2, and let's solve for n. Well, there must be n plus 1 lots of this to get the number of hydrogens correct, and there must be n lots of this to make the carbons correct. So what that tells me is that 5 is equal to 10 oxygens on the left, 2n oxygens from that, n plus 1 from that, so it's 3n plus 1, and we can clearly see that n is equal to 3, so it's C3H8. I quite like that. That was fun. Nice. Very ESAT problem solving. Here, 1.2 grams of a metal hydroxide. You really do start to spot them, don't you? Because that is just that times. So it's a 1. And that is just 2. So it's 0.02 moles is required to exactly neutralize a solution containing that much sulfuric acid. Well, let's work out sulfuric acid, H2SO4. So it's 2 and 32 and 64 is 34, it's 98. So therefore that's 0.01 mole. So therefore it's a 2-to-1 ratio. Using Q as the symbol for the metal, it means there are 2 Qs reacting with the H2SO4 to give me, I think it's going to be Q2SO4 plus hydrogen there. And the reason why is because what it's doing is it's displacing the hydrogen to form the H2. How do I know this? Well, we need 2 Qs to react with the SO4, which forms a 2-, and the only way that's possible. So to me, it's just intuitive, but I'm hoping it's intuitive to you because yeah, it just is because we need 2 of them to neutralize the acid. And I know metal plus acid goes to salt plus hydrogen. I know all of that metal is going into the salt. I know there were 2 of them, so they have to go into the salt, making it Q2. I think that's my favorite explanation there. Working in solutions. So what's the concentration in who works in grams per decimeter cubed? But it's a good thing I read that because otherwise that would go really badly. I'm trivial. I can't even be bothered. You just divide the 2 numbers. That's no. Calculate the mass of sodium chloride required to make. There we go. So that is 0.25 decimeters cubed. And there's 9 grams per that. So it's 9 over 4, which is 2.25 grams required there. Not too bad. Moles per decimeter cubed, obviously much more the done thing where you're being careful about your units. So that's 0.75 decimeters cubed times that is 0.075 mole. Oh, God. All right, so 23 plus 1 plus 12 plus 48. That makes 60, and that is 84. And we want that, 0.75. So it's 8.4 times 0.75, which is 3/4. Makes that 2.1, makes that 6.3 grams. Cool. I just think this is going to be the better way to go about this. Rather than just sort of go down the thing and sort of talk about it hypothetically, I think demonstrating the skills is better than just talking about the skills. So here, what's the concentration in moles per decimeter cubed of a solution formed when this much potassium hydroxide is dissolved in this much volume? So again, let's work out the potassium hydroxide. Potassium is group 1, which means it is KOH. If it was magnesium, it would be MgO2OH twice. So here we just add them together. So 40 and that is 56. Nice, which means that's 0.1 moles in half a decimeter cubed. So in 1 full decimeter cubed, there would be 0.2 moles per decimeter cubed. Yep, N equals CV. We know this. So determine the amount present in this. It would have been really helpful if they actually told us how many decimeters cubed there were. Just saying. So we'll skip debate and say this. So that is 10 times 10 to the minus 3 decimeters cubed times 0.25. So you get 2.5 times 10 to the minus 3 moles of sodium hydroxide there. Calculate the volumes. So N equals CV. So V equals N over C. 0.1 all over 0.05 is 10 over 5 is 2. So here, volume is number of moles over concentration. So you get 2 times 10 to the minus 3 all over 0.08. Multiply top and bottom by 100. 2 times 10 to the minus 1 all over 8. Apologies for the bell. I will not be answering that. I can guarantee it's not for me. So let's call that 20 times 10 to the minus 2. And then let's do that. So it's 2.5 times 10 to the minus 2. Maybe it is for me. It's never for me. All right, guys, I'm going to pause. I'm going to be right back just in case it is for me. Be back in a sec. Oh my God, guess what? Not for me. Never the case. I'll scrub that out in the sort of video after the fact. So these are all going so super well. What volumes of the volume concentrated solutions are required to give the stated volumes of more I'll just answer the question. So what volumes of the following are required to give the stated volumes of more dilute? Okay, so let's work out. So that means that's a quarter of that. So we want 1 mole. So to get 1 mole out of that, well, N equals CV. So the volume is N over C, which is 1 mole out of the 2. So we need 0.5 decimeters cubed. And then we dilute it with 3.5 decimeters cubed of water. Here, that is a quarter of a decimeter. So again, that's 0.5 moles of this thing. So we want 0.5 moles from that. So it's 0.5 all over 2.5, which is 5 over 25, which is 0.2 decimeters cubed. In other words, 200 centimeters cubed, and the remaining 50 is the water that you dilute it with. Titration calculations. So first thing you need is an equation. So we have sodium hydroxide and hydrochloric acid. We know that's going to go to NaCl and water. So it's a very simple 1-to-1 ratio all across the board. Work that out. So 20 times 10 to the minus 3 decimeters cubed times 0.1 is 2 times 10 to the minus 3 moles of hydrochloric acid. Therefore, that exact same number of moles of this. So it's 2 times 10 to the minus 3 moles in 25 times 10 to the minus 3 decimeters cubed is 8 over 100. So it's 0.08 moles per decimeter cubed, which I'll call big M because lazy. Okay, so here. Oh, okay, so sodium hydroxide and sulfuric acid is going to go to, now sodium is plus, so 2 of them are required to balance the SO4 2 minus, and a water, so there's got to be 2 of that and 2 of that. Now we're balanced. So we have 50 times 10 to the minus 3 decimeters cubed times 0.1. So 5 times 10 to the minus 3 moles of sulfuric acid. And therefore 10 times 10 to the minus 3 moles of sodium hydroxide. Volume is moles over concentration. So that's 200 times 10 to the minus 3. Cancels, 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 cancels. 0.05 decimeters cubed is 50 centimeters cubed. Okay. I'm really curious to mark these up actually at the end. So what volume of aqueous? So again, we've got sodium hydroxide and hydrochloric acid. Nothing special there. NaCl and water. Here, 25 times 10 to the minus 3. You get real, like these just become so quick, don't they, after a while? So that's the number of moles of hydrochloric acid. So it's also the number of moles of sodium hydroxide. Oh, don't grams per decimeter cubed me. Well, hold on. Let's work out the... fine. So 1 mole of sodium hydroxide. I'm going to have to... Where did I last see what these MRs are? So sodium hydroxide 24 is 40. So 20 grams is 0.5 moles per decimeter cubed. And we have the number of moles, so then we divide by the volume, which is 0.5. So it's 5 times 10 to the minus 3 decimeters cubed, or in other words, 5 centimeters cubed. Okay. Saturated solutions are fully dissolved. So if you try to add any more, then no more will be able to dissolve beyond that point. It will just settle to the bottom. Solubility curves, you don't really see them that much. All right, so we got 250 centimeters cubed, which means 250 grams of water. So if it's 73 over 100, we have to multiply top and bottom by 2.5. So 73 times 2.5 is something I still cannot be bothered to calculate. It's whatever that is. That's how you do it. No, I'm not going to, no, hold myself to a higher standard. I'm not going to demonstrate laziness. So 73, 2.5. That's a 2. 6 for 1. There we go. That is the mass that will dissolve in 250 centimeters cubed. Okay. Using the following solubility curve, what mass of copper 2 sulfate will be precipitated out? Okay, at 74. If a saturated solution in 50 grams of water at 74 degrees. So at 74 degrees, I'm just going to call that 50. So 50 grams would have been in 100 grams of water. So 25 grams would have existed in 50 grams of water. If we're cooling it to 24 degrees C, it's now going to be 22 grams per 100 grams of water. So 11 grams in 50 grams of water. So there were 25 grams. Now only 11 grams of them get to stasis, dissolve, so 14 grams get precipitated out. That one's probably the new one for you guys. So hopefully that made sense, the logic of what I just did. If there's any difficulty, I think it's there. Percentage yield is actual over theoretical times 100. So here we have a mass of ethanoic acid formed from the oxidation of that much ethanol, C2H6O, 24 and 6 and 16 is 46. 23, so that's 0.5 moles of ethanol. Which should have yielded 0.5 moles of this thing. In practice, we have C2H4O2, 28, 60 is the molar mass of this. So we should have made 30 grams. In practice, we made 25 grams, so the percentage yield is 25 over 30 times 100, which is 5/6 times 100, which is 83.3% is the percentage yield. Exercise 50, so the reaction of nitrogen with hydrogen, under certain reaction conditions, the percentage yield is 15%. What mass of ammonia is formed when that much nitrogen? So 2.8 over 14 is 28 times 0.1, all over 14, so it's 0.2 moles. Reacts with excess hydrogen, so that 0.6 moles of hydrogen get formed, and 0.4 moles. Theoretically, if it fully converted, which it doesn't, so theoretically, it should be 0.4 moles. In fact, only 15% of that gets converted. So 0.4 times 0.15 is 60 over 1,000. Is 6 over 100 is 0.06. Okay. In practice, that many moles gets created of ammonia. The molar mass is 17, so it's 0.06 times 17. 1.02 grams, I think. Here, if the percentage yield is 50%, what's the mass of ethanol that must be reacted with excess ethanoic acid to form this? Ethyl ethanoate, right? 1, 2, 3, 4, 48. 1, 2, of those makes 32. 3, 5, 8, 40, 88. 4.4 over 88 is, again, so it would be 0.05 moles of that thing. But the percentage yield is 50%, so it should have been 0.1, which means this should have been 0.1. And we do 0.1 times. Now, what's the, so ethanol, mass of ethanol. So the ethanol is C2H6O, which is 30, so it's 46. So it should have been 4.6 grams of ethanol. Cool. All right, so that times 0.2. So 32, 180, 261. Do you know what I'm going to have to do? Is I'm going to have to open a second one of these. And I'm going to scroll it down to the answers. And I'm going to go split screen on this. Okay. So let's zoom all the way back up to 21 and just sort of review the different skills in this chapter, because this is one where it's really done by demonstration. Like talking about it in theory just was never ever going to cut it. So this was just that times 0.2. Yeah. Then we got 32, 180. I corrected that to 261. Couldn't be bothered to work up the molar mass of that. So we've got 4 kilograms. On the second one, again, I couldn't be bothered to look up the molar mass. So here, percentage by mass of carbon in this is 40%, it looks like. Yep. Let me zoom out just so I can see it a bit better. Okay, so because I just want to make sure I didn't do anything stupid at any point. So 26, 67.5. Did I engage in silliness? I did engage in silliness. That was entirely doable. Because I could have gone further. I could have spotted a 3 would make that a 2 and a 27. So it was 27 times 2.5. So it's 54 plus 13.5 is 67.5. So I could have got that percentage, actually. Should have followed that through. But the theory was right. Here it's 1-to-1. 28, they just copied the equation down, like it was just the same question. C2H2O4. Exercise 30. 0.2 grams. Massive calcium carbide. I said it was 12.8 kilograms. Good. This one, 12.5 decimeters cubed. Good. The mass of this, I said, was 2.675. Good. 1.2. Good. 35. Yep, nailed that. Yeah, it's cool that you don't really get to see that as much in A-level. It's a bit more ESAT, working with algebra in your chemistry equations. Very much enjoyed that one. So 36, yep, nailed that. Could not be bothered, that was too easy. That was genuinely too easy. 2.25, good. 6.3, good. 40, good. 41. Would have been good if they'd actually given me the decimeters cubed there, so that's completely fine. Here, so 42, it looks like. Yep, 43. 0.5, 0.2, yep. Here, 0.08 molar, yep. 45, yep, 50 centimeters cubed. 46, 5 centimeters cubed, yep. Then the solubility stuff. So 14 grams falls out. I overshot the mark a little bit, but yes, 14 grams crashes out. 83.3%. Uh, 0.51 grams. Oh, it's off by a factor of 2. Oh, wait, no, hold on a minute. I did do something silly. What did I do that was silly? Why was I out by a factor of 2? Hold on a minute. The percentage yield is 15% of nitrogen. Oh, okay. Sorry, that was silly on my part. I divided by 14, which is a single nitrogen. In fact, I should have divided by the MR of N2, which is 28, and that's why this went wrong. That was actually 0.1. That was actually 0.2. That was actually 0. See, sneaky that. I really got called out there. So 4.6, all good. Great. All right, so let's full screen this again. So just that one correction there. And that's why I wanted to correct it, right? It's so easy to make these teeny execution errors in chemistry. All right, oxidation, reduction, and redox. So C.5. How much left of this do we have? C.5, C.6, 7, 8, 9. Damn. All right, maybe. Okay, looks like we're just gonna be getting through this. I don't think we're gonna have all the time, guys, to do a lot of past papers. There is so much in here. Jesus. Oh man. Maybe I should plan this a lot better. Because I've been. All right, let's race through. So that was the quantitative. But in the quantitative, in my opinion, is genuinely the most important. So here, oxidation is gain of oxygen. Also oil rigs. So oxidation is loss of electrons. Reduction is gain in electrons. Oxidation states in organic compounds. You can kind of do that by its ratio with known ions. So if I let's go to 5.3 here. So examples. Use oxidation. Remember that if it's an element, the oxidation state is 0. And if it's an ion, it's what you think it is. So K is +1, I is -1. Here, I goes to 0, bromine goes to -1. So here, iodide has lost an electron. Oil rig, iodide has been oxidized to iodine. Bromine has been reduced to bromine 1-. In which two of the following species does nitrogen have the same oxidation state? Well, oxygen is always 2-, right? So here the N is +2. Here the N is +4. Here the N is +1. Here the N is -3 to balance with the 3 1+s. Here that's +1, that's -4 overall. So we need a +3 to balance that out. Okay, so these are -6 over, so that has to be +5, so that when you bring in the -6s, that makes you -1 overall. Here, that is, magnesium is +2, so that's +6 overall, so that's -3. So in these two, the nitrogen is the same. So that's kind of what we're talking about with oxidation states. So disproportionation is when the same species is both oxidized and reduced in the same reaction. So here, one of the oxygens gets oxidized and one of them gets reduced. So it is simultaneously oxidized and reduced, which is what disproportionation is. Then oxidizing agent is the thing that oxidizes the other thing, and the reducing agent is the reactant that reduces the other reactant, right? So oxidizing agents get reduced and oxidize something else. Reducing agents get oxidized and reduce something else. Structures bonding and hope you guys paid attention in GCSE. Structures bonding and properties. So elements, compounds, mixtures. I'm going to leave that to you. Okay, so we know that metals like to lose electrons, non-metals like to gain electrons. If you have a metal-metal, that's a metallic bond. Metal-non-metal, that's ionic bond. Non-metal-non-metal, that's covalent. Metallic bonding is the electrostatic attraction between a lattice of positive metal ions and a sea of delocalized electrons. Ionic bonding is the electrostatic attraction between oppositely charged ions. Covalent bonding is the electrostatic attraction between positive nuclei and a shared pair of electrons in between. So for ionic bonding, they're transferred. Yep, you can predict what ions are going to form. Okay, so when you're in a transition metal, the Roman numerals tell you the oxidation state. So here that means Fe3+, you know that. Formula of ionic compounds and their constituent ions. It's pretty simple, but let's try that. So 6.3. Let me do some demonstration. So where is that? So 6.3. Here we go. Give me some questions to demonstrate the skill here. Ionic structures. So sodium bromide, yep. Metal, non-metal. No, that's covalent. 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 Ionic. Ionic. That's zinc. With that, it's as long as it's not aqueous. And that is covalent. So here, iron 2 oxide is going to be FeO, because oxide is 2- and that's 2+, so they balance. Here, potassium is +1, nitrate is -1, so they balance in 1-to-1. Magnesium is 2+, fluoride is -1, so we need 2 fluorides to balance. Calcium is +2, hydroxide is OH-, so we need 2 of those to balance. Aluminium is Al3+, sulfate is SO4 2-. In order to balance these, we need 2 of the aluminium and 3 of the sulfates. So just worth bearing that in mind. General physical properties of ionic compounds. They have high melting points and boiling points because of the strong attraction between the oppositely charged ions. They conduct electricity when molten or aqueous because the charged ions are free to move. They do not conduct in a solid state because the charged ions are not free to move. Those are the important ones. Covalent bond, I've discussed. So you either have simple molecular with weak intermolecular forces between the molecules, or you have giant covalent structures, as is the case with diamond or graphite or silicon dioxide. Simple molecular structures have low melting points and boiling points due to the weak intermolecular forces, which require not that much energy to overcome. Diamond and graphite and the giant structures have high melting points and boiling points because in order to melt them, you need to break all the covalent bonds, which are very strong and require lots of energy to break. So graphite has layers of electrons that can slide past each other, making it slippery. Diamond has a 3D structure because it's bonded to 4 other carbons, meaning it's got strong covalent bonds in all directions, meaning it's quite hard. Graphite also has a sea of delocalized electrons, so charged particles are free to move, so it can conduct electricity. Diamond does not conduct electricity. All of the electrons are locked into the covalent bonds. Nice. Metallic bonding, we've discussed. Physical properties. They're malleable because the layers of atoms can slide over each other. That is less true if you put if you alloy it. So you put different sized atoms in the structure, which makes the layers harder to slide over each other. They have delocalized electrons, which are free to move, so they conduct electricity. Yeah, this is fine. Group chemistry. Physical and chemical properties of the alkali metals, the halogens, and the noble gases. I think a lot of this is just memorization. So the halogens, they get darker in color as you move down, and they go from gas in fluorine and chlorine to liquid bromine to solid iodine. Noble gases, they're all gases. They also don't react. Halogens, they gain one electron. They do the displacement reactions, all that kind of stuff. So all the GCSE chemistry stuff. Trends in reactivity, we've already discussed. Halogens, we've also already discussed the trends in reactivity. A displacement reaction is when a more reactive element displaces a less reactive element from its compound. In group 7, because you're trying to gain an electron, that makes it more reactive going up the group when the outer shell gaining the electron is closer to the nucleus, so has a stronger attraction for that electron coming in. And so something like chlorine will displace iodide from its compound. And that will also result in a color change of the solution. So let's get an example of that. So 7.3. Are they going to give me... Where's... Oh, no. Did I overshoot the mark? I didn't actually. Okay, here we go. None. So iodine is less reactive than chloride, so it does not displace. Bromine is less reactive than chloride, so it does not displace. Chlorine and chloride, nothing would happen there. So that was a bit of a silly question. But maybe that was the point, is to trap you. Separation techniques. So you have filtration of that separates an undissolved solid from a liquid. You have fractional distillation when you're separating two liquids and want to keep them both. You have simple distillation, which is when you kind of get rid of one liquid from the solution. Or like for instance, if you want to get the salt back from a salt solution, you would distill off, or that might be evaporation. You also have chromatography, separating dyes, all this kind of stuff. You can use RF values to see which dyes are in different things. That's very GCSE. I think you guys know that. Centrifuge. Oh, let's talk about centrifugation. That I think requires a little bit. So let's talk in more detail about this stuff. Oh, so electrolysis they've got in there, but we can probably talk about that later. Physical processes. Decanting, filtration, separating funnel, distillation, fractional distillation, evaporation and crystallization, and chromatography, where you compare using RF values. Now this, it's used to separate heterogeneous mixtures. So that's mixtures with more than one thing in it, based on their differences in particle mass. It can be used to separate mixtures of a gas, but it is more commonly used to separate solids from liquids or solutions. If a liquid is mixed with a solid, the solid settles to the bottom of the container because they're more dense. When it's smaller, finely divided, random motion and collisions causes them to settle much more slowly, and in some cases they do not settle, they just hang. So centrifuge, put it in a centrifuge, it'll force. So for instance, that's the case with blood, where you have the solid red blood cells sitting in the liquid of the plasma. You stick that in a centrifuge, it'll force the solid red blood cells to the outside and the plasma sort of more towards the center. Okay. Yeah, there we go. Red blood cells and from the remaining plasma. Okay, so acids, bases, and salts. We've been through the neutralization reactions. Acid plus metal goes to salt plus hydrogen. Acid plus base goes to salt plus water. Acid plus carbonate goes to salt plus water plus carbon dioxide. Strong means it fully dissociates. So for instance, hydrochloric acid fully splits up into H plus and Cl minus. Weak acid, classic ethanoic acid, it only partially dissociates in an equilibrium. Dilute and concentrated have to do with the amount or the sort of concentration of H plus ions present in your solution. Yes, so metal oxides form basic solutions when they dissolve in water. Non-metal oxides form acidic solutions when they dissolve in water. pH is a measure of H plus. It's logarithmic. Okay, I'm happy with that. Bases, same thing. Same thing. Yeah, okay. Rates of reaction. So the qualitative effects of a rate of reaction, okay, you increase the concentration, you increase the rate of reaction because there are more particles in a given volume, which means there are more collisions per second, so more successful collisions per second, so a bigger rate of reaction. Temperature affects it for two reasons: more collisions per second, and a greater percentage of those collisions have enough energy to overcome the activation energy. So therefore, a greater proportion of the collisions will be successful, and there are more collisions to start with. So more successful collisions per second, and therefore the rate of reaction increases. Particle size. So the finer the thing, so the bigger the surface area of a solid, the bigger the rate of reaction because you get more collisions. Catalysts decrease the activation energy. So it does not change the number of collisions, but it does change the proportion that are successful. And for gaseous pressure, increased rate of reaction. So you can measure the loss of reactant or the gain of a product in mass or moles measured over time. And importantly, guys, the rate of reaction is given by the gradient at the start. Use collision theory. Yep, we just discussed that. Yep, 10.5, we just discussed that. Activation energy on an energy level diagram. That would be the activation energy. That would be the enthalpy. This would also be for an exothermic reaction because it overall gives out energy. Catalysts are not used up in a reaction. That's important. They are chemically unchanged, provide an alternate route, and do not affect the position of equilibrium. That's fine. So energetics. Exothermic reaction gives out energy. Endothermic reaction takes in energy. Yeah, this actually isn't too bad. Okay, let's go to 11.4. That's what I'm going to have to demo. Where is 11.4? I think I have overshot. I know I have overshot. That's 12. Come on. Come on. Give me a thing that lets me know where I am. Okay. Oh, you just throwing them all in. Great. Love that for me. Okay, so let's do some calculations we're given. Okay, so you can do it one of two ways. You can either do it from the bond enthalpies, if given. That's insane. They're not giving me the data. I would also, it's rare for bond enthalpy to come up. If I ever saw bond enthalpy in a ESAT, I would immediately make that a second pass question. But in theory, you calculate. So remembering that breaking bonds is endothermic and making bonds is exothermic. It's all the bonds broken minus all the bonds formed. And you have to calculate that. It's super easy to miss out on a specific bond, though. Okay. Q, if you're doing it for using calorimetry, Q equals mc delta T. You divide by the number of moles to get the enthalpy change. That assumes all of the energy goes into the thing, but it doesn't actually happen. In practice, you're only picking up a small amount. Well, not the small. You're picking up less than the true amount of the enthalpy given out. So you calculate a smaller enthalpy change than the true enthalpy change. So for instance, let's talk about this. So Q equals mc delta T. So that's the mass of the water. So the total mass of water is 75. And it's 4.2 grams per centimeter cubed in chemistry. That's 4,200 in physics. And the delta T here is 5.6. That's a really ugly number. In the interest of time, I'm just going to type it in. In practice, they would give you better numbers than this. This is 1764 joules are released. The enthalpy change per mole of water produced. Well, we have sodium hydroxide and hydrochloric acid, which is clearly just forming NaCl and water. Now we have to work out how many moles of water are produced. So that's how much. So what we're going to have to do, actually, let's work this out. So this is 35 times 10 to the minus 3 decimeters cubed times 1 mole per decimeter cubed. So that's the number of moles of sodium hydroxide added to. So clearly, there is less of the sodium hydroxide. So what's going to happen is the HCl will be in excess. The sodium hydroxide will be the limiting reagent, and it will form 35 times 10 to the minus 3 moles of the water. So that 1764 is divided by the 35 times 10 to the minus 3 moles of water that are formed. And you get a number which they did not make nice for you, which is rude, but it's 50.4 kilojoules per mole. So worth demoing that. You work out Q equals mc delta T to get the energy and divide by the number of moles, being very careful that the mass is the total mass of water present in the reaction when everything is added together. Let me just check that 97, actually. You're not going to tell me what the answers were? Oh, yeah, 50.4. Good. Okay. Okay, so electrolysis. What you have to know here is that positive ions, positive cations are going to go to the negative cathode, where they will pick up electrons and form elements. Negative anions will go to the positive anode, where they will lose electrons to become elements. If you are competing, as is the case with solutions, then the more reactive ion wants to stay in solution more. And so the less reactive ion is the one that comes out. You work out the reactivity from the reactivity series. So in general, good rule of thumb, hydrogen is coming out unless there is copper present or silver or gold. Oxygen is coming out unless there is concentrated halogen, is a good rule of thumb. DC current is used because that enables If it was AC, then the ions would be like, wait, where am I going? And they wouldn't actually get there and transfer their electrons, and it would just be bad. Although I'm curious if they have an explicit explanation for that. Not really. Yep, so we talked about 12.3. Let me demonstrate some 12.4 here. So here, a nickel jug is to be electroplated with silver. Would be suitable. Here, the electrolyte, that's not suitable. There's no silver in there to plate. There's no silver in here to plate. So here we want, so the silver is silver plus. So it's going to go to the negative electrode. So the nickel jug has to be the negative electrode. That will work. And out of the positive electrode, you're going to get oxygen produced from the water in the solution. The nickel jug can never be positive. Here it doesn't work because there's no silver in the electrolyte. Here this would work. Okay, so purification of copper. Nope, that's it. All right, maybe I'll get to demo that. In fact, I'm rushing through this actually quite well. Said that I'm getting to organic, and I think there's more besides this. Okay, maybe not. Yeah, we're just gonna get through this. I demo it another time. Like a full run. So organic chemistry. So crude oil, fractional distillation, hotter at the bottom, colder at the top. There's a temperature gradient. It's vaporized before it goes in. Because it's a hot gas, it rises. When it meets its boiling point, it condenses to a liquid and gets siphoned off according to its liquid point, which varies according to chain length. Longer the chain, the stronger the intermolecular forces, the higher the melting point and boiling point, therefore the lower out the column it comes. So it sort of divides it by chain length. So as you move down the column, they get higher boiling points, more viscous, less flammable, also less volatile, I suppose. You use the longer chains, you crack them to form shorter chains that are more in demand. And you always get the shorter alkane as well as an alkene. Structural isomers are same molecular formula, different arrangement of atoms in space. So different structural formula or displayed formula. You can have branch isomers and what do they call it? The functional group isomers. So if the oxygen is in a different way, that changes the functional group. Complete combustion goes to carbon dioxide and water. In the presence of a lot of oxygen. Incomplete combustion can form carbon monoxide or soot, carbon, and water. Balanced symbol equations, naming stuff, homologous series, alkanes, alkenes, that kind of thing. I think you know this. Alkanes, general formula, yes. Methane, ethane, propane, butane, pentane, hexane. That's fine. Alkenes, yep. Yeah, they have a double bond. The test for alkenes is bromine water, which is normally orange. In the presence of an alkene, it will absorb you undergo an addition reaction where the bromine adds across the double bond, is removed from the bromine water, so it decolorizes it. Addition reactions, there are lots of things that can add across the double bond. So hydrogen, halogens, all these kinds of things. Yeah. So, I mean, let me know if your organic isn't great, and we can do a bit more detail on that. Polymers, always remember that your monomer has to be written in this form with the bits on the side and the double bond in the middle, ready to form that chain. If it is in any other form, you need to first rearrange it into that form before you undergo the addition reaction. Okay. Condensation polymers, that's done where instead of it being sort of an addition reaction of double bond to double bond, you have, for instance, polyesters, which have carboxylic acids and alcohols forming an ester link. You need to have two functional groups on each monomer thing in order to keep the chain going. Or you can have polyamides, which is, what is that again? That's carboxylic acid and an amine group, which is NH2. In all of these cases, a small molecule like water falls off. Biodegradable, yeah. Alcohols have an OH group at the end. Ooh, describe the reactions of alcohols with sodium metal. I actually don't know that one. Let's go get there. So 13.5. Did I see some? Oh, that's reactions of alkenes. Yeah, you add stuff across the double bond, you're fine. 13.4. You get a bunch of nastiness. 13.5. C. To whom are you teaching, bro? So this is for people doing ESAT. So this is for people going for, well, I suppose if you're doing chemistry, typically you're going for Cambridge NatSci and you're wanting to do chemistry as your science within the ESAT past paper. So this is for people going in there, sort of like 17-year-olds about to apply for university. So a lot of this stuff you will have covered at GCSE, which is why I'm kind of racing it and just sort of covering the bases. And the ESAT, it's a really fun paper because of how fast you have to go. So the syllabus has to be completely mastered in order for you to go at like top speed. And I really want to get, okay, so the reaction of alcohols with sodium. So when sodium is added to water, the reaction is fast and vigorous, where the sodium displaces the hydrogen because it's more reactive to form sodium hydroxide and hydrogen gas. When it's added to ethanol, the reaction is much slower and more moderate. The products are hydrogen gas and this thing, so it still displaces a hydrogen, specifically the hydrogen from the alcohol. It happens a lot slower. So I think this is worth knowing. Yeah, thank you. Shall keep going. Apologies if it's not what you need right now in your educational journey. So here we got the sodium displaces this hydrogen. You get this thing formed. It's important to know it's much slower and more moderate than the reaction with water, which is also a strong alkali. And it can be a test for OH groups in alcohols. It can also be used as a means for safe disposal of sodium. Okay. So that's something I wouldn't have known. So I'm glad I looked that up. Which country? So I'm originally from America, but this test is for university entrance in the UK, where I now live. So this is for, yeah, very much UK students. Although I do have a number of students internationally who do things like the IB, who would take this paper to move into a UK university. So a lot of people would sit the ESAT to get into like Imperial for engineering, for instance. But again, for chemistry specifically, you're more talking about getting into Cambridge. Or maybe now Oxford. I am curious, actually. You're right. I need to look that up, whether Oxford have started taking the ESAT. I know they do for their physics students who would normally have taken the PAT test, but I'm curious if their chemistry is taking that. Okay. So carboxylic acids, we have your COOH group where the H can fall off in partial dissociation to form an H+, making this an acid. It undergoes all of the reactions that acids do, but can also react with alcohols to form an ester. Okay. Not too bad. Metals. Oh, you're from India. Okay. You're very welcome. Welcome to stick around. Decide what you like to see, because most of my stuff is more math and physics. Lots of it is on exam technique, so it's lots of me sort of demonstrating stuff as opposed to like pure teaching. So kind of stick around for that if that's your jam. Have a Discord if you want to get notified on when I do stuff. Have a good rest of your evening. Right, so metals. Reactivity of metal, it forms positive ions by losing electrons. As we said before, well, we've already spoken about what things will go more reactive as you go down a group because it's easier to lose the electron. You should also have a vague sense of the order of reactivity, which you can find in sort of any textbook. How metals are related to their physical and chemical properties. Alloys can be formed, yeah. Oh, the extraction of metals is important. So if you are more reactive than carbon, if carbon is more reactive than the metal, then carbon can be used to displace the metal from its ore. So this is the case of burning iron ore with carbon in order to produce iron. If you are more reactive than carbon, you cannot use carbon to reduce it. You instead need to use electrolysis, as is the case with getting aluminium out of aluminium ore, or aluminum, as I like to say. Common properties of transition metals. They form multiple oxidation states. They form colored compounds. They are used as catalysts. Kinetic particle theory. We've kind of already spoken about that when it comes to rates of reaction. I honestly think there's not much to say here. So this is just the arrangements of in solids, liquids, and gas, which I think is pretty standard. Chemical tests, I promise you I will never learn these. You got to, though. I don't have to. This is, to me, is just knowledge. It's not understanding. It's not the fun stuff that I like to do, which is why I kind of tend away from the chemistry and more towards the math and the physics where it's more understanding based. But hydrogen, you've got your squeaky pop. Oxygen, relights glowing splint. Carbon dioxide turns lime water cloudy. Chlorine turns damp red litmus paper red, then bleached. Sorry, damp blue litmus paper red, then bleached. Carbonates use a dilute acid. They form bubbles, which you can, again, bubble through lime water, which will turn it cloudy. Halides, you use silver nitrate solution, which will turn it a white precipitate or cream or yellow. Sulfates use barium chlorine to get a white precipitate. Positive ones, you can use aqueous sodium hydroxide to get specifically colored precipitates, or you can use a flame test. Yeah, not a bother at all. Sorry, another comment question. You're preparing for the JE. Let me read this in a bit more detail. So you were taught to, while preparing the GG. Okay, so it was taught to you when you were in 12th grade while preparing for the JAE, which is a very like Indian-specific test for getting into university. This next version of this, is this useful for real life? I mean, what part of it is useful for real life? So in my life, I don't need to know the specifics about the flame test, which is why I don't know them. But or you could think of it in a more abstract sense, like applying yourself to the task of completing a test. I have to meet this objective external standard. These are the steps I need to go through to meet that objective external standard. Can I discipline myself enough to take on the information to be able to perform in the moment? That is super transferable and is something you're going to be able to take with you in life. So it's kind of just your way of thinking about it. So it may be a direct, yes, you use this because you do chemistry in your day-to-day life, or it's indirect because of the skills you gain in being able to perform well at your best. So that's what I'd say. Right, getting back to these chemical tests. I just realized when I split screen before, I really don't think you guys could see both, but I marked it, so it's fine. Did I? I don't know. Okay, I'll go back and check. So flame tests. Know them. I refuse. You must not. Presence of water. Anhydrous white copper sulfate. It goes blue. Air and water. Air is 78% nitrogen, 21% oxygen, 0.9% argon, 0.09% carbon dioxide, rest trace. These things increase, that's global warming. Origins and effects of these things that kill you. Remember as well, the non-metal oxides form acids when they dissolve in water, so they are responsible for acid rain. Know the purpose of chlorine and fluorine ions in the... No. Chloride, I suppose, in drinking water, it's sort of like, why? I don't want to know that. No, thank you. No, chlorine disinfects it, and fluorine is good for teeth. But why is that in the ESAT spec? Excuse me? Are you serious? Hold on a minute. Hold right on a minute. Are they actually... Oh, that's okay. Well, I'm very welcome to have you when I'm around. It's nearly bedtime for you, though, if you're in India. So you should sleep it off. Right. So chlorine sterilizes it, and fluorine is good for tooth decay, which apparently is a relevant thing. All right. How am I feeling, guys? Go on. It won't take long. Let me quickly pull up. Because we may as well, while we're here, one and done. Let's just get it done. So NSAA past papers. I'm going to use NSAA section 1. I'm going to take the latest one available. I'm going to take 2022 because I remember that's when they were the hardest. Let's take on the chemistry. Now, let me time it. This is genuinely just out of curiosity. So I'm already like an hour and 45 in. So I'm not sure my brain is going to be an absolute peak. But I'll take my split times just so I can kind of get a sense of it. Now I'm going to do what I did do as always. Because I also haven't, I'm going to have fun with this. Like the, oh, trust me, overthinking about the future, not worth it. Like, you know where you're going to target. You know what you have to do the things, and keep yourself in an optimal mental state to be able to do the things you need to do. Then you'll be fine. I will also say when it comes to university entrance, you typically end up where you're supposed to end up. There's very few people who genuinely should be somewhere other than where they are. So as long as you hold yourself to a high standard and go away having no regrets let's have this conversation, because university entrance is a really stressful time because it really affects your sort of longer term life path. I think what you really want to avoid is a situation where you're beating yourself up that you could have or should have done better. So that's why you prepare as hard as you do, putting in a sort of good bid so that you go in, do your absolute best, and that way you don't beat yourself up afterwards. You kind of say, all right, I literally couldn't have done better than that. So whatever I get is where I'm supposed to be. And that's what you want. That's what's in your control, is having a no regret strategy where you think so you can, before you walk in, you can look back and go, okay, I know why I did everything I did to get to this point. I trust my preparation. I trust that I couldn't do better. Let's go in and fight for every mark I can possibly get. And if you walk out executing good exam technique and not knowing where you've lost your marks, there's nothing to regret, and the outcome must be good. So I think that's just a very helpful way to protect yourself and your sort of mentality as you move through this. No regret strategy. That's first and foremost what you want to be doing. No, what do you like? This is live streaming. This is a chat. This is the thing. People who show up and chat to me are the ones who get to kind of dictate what we're doing. This is not me sort of like, this is not the disturbing. This is the entire point. Please disturb, because you are never, ever going to be the only one thinking the thing that you're thinking. So by bringing it, it will be instructive to not just you, but other people as well. The JEE. One thing I will say in your defense, the JEE is notoriously difficult. Like, I keep on having people in my chat who are trying to get me to do the JEE advanced, and I would just look at it and I'm like, no. No, I won't. No, but thank you very much. So no worries. I'm sure you will land on your feet and sort of find the right way forward. I will also say for people who don't get where they want to get, think about the alternative. The alternative is, let's say you worked 8 hours a day just to maybe scrape in. That's how much you have to work just to get by. Like you, wherever you end up, you don't want to be on the bottom. It's much better for you to be at the top third of a university that's not your top choice rather than be scraping at the bottom of one and then you feel like you're awful and like can't get by. So it might feel bad in the moment to not do well in the JEE and not get the university you want, but it would be even worse if you scraped in somewhere and had that feeling forever for the entirety of your degree. You come out the other side feeling really stupid and unconfident. That actually can affect your job prospects more than not getting into your top choice university. So again, land where you're going to land, stay confident, like work on a life path that makes you feel like you were kind of where you're supposed to be, and don't let yourself get dragged off what you're supposed to do, is my sort of general advice. Yeah, that's crazy. You got 97%, but due to a category issue, you failed. How is that even possible? What do you mean by a category issue? Do I need to like learn about this JEE? Because I hear things about it, man. Like it's what do you mean category issue? How could someone get a 97% but fail with 97? No, I don't trust that. What's that? Yeah, studying that much and getting bad sleep is just not it. It ruins your life. Category issue. That's so bizarre. Right, what I'm gonna do now though, I'm gonna start ignoring the chat for a bit, so please excuse me, mainly because I'm gonna focus on this. I'm gonna move to the chemistry part, and I'm going to use this multiple pass strategy for multiple choice, which is if I like the question and can do it quickly and accurately, I will do it immediately. If not, I will skip it and move on. Now, let me check. So there are 20 questions, it looks like. So at 90 seconds a question, I should take half an hour. I shouldn't really be starting this now, but hey, I'm here. Let's get it done while we're here. Alrighty then. So oh, I hate that. In India, the cutoff rates varies based on which community you belong to. The caste, I think the caste system is so diabolical, just absolute nonsense. I do not get why you would take someone with potential and refuse to harness that potential because of a completely arbitrary set of criteria. It makes no sense. And I think that's why a lot of students in an Indian system look elsewhere. I have a lot of people from the sort of global Indian diaspora trying to take these sorts of tests to get into UK universities for exactly that reason. It makes no sense. Nah, sorry, man. 97%? That's not a you problem. That's a them problem. Like, So half an hour on the clock. I'll take my split times. I'm going to start sharing the window. Are you looking at it? Yes, you are. All right, I'm curious. Let's see what happens. Video editing. That's not bad. You know what? Actually, learning a skill and stuff, like keeping yourself employable, the way to go. Not bad, but right. For half an hour, though, you'll get to watch me go at absolute maximum speed. Have fun. This is if you haven't seen this before, me going at full speed is kind of wild. Even like 2 hours in. So ready, start the clock. Let's go. Right. So, oh wait, no, stop. No, hate this, stop. That's not what I should do. I should always download it. Apologies, because what I'm going to instead is I'm going to go and I'm going to open it in a different application so that I can actually annotate on it properly. Apologies. False start. Take two. Reset. So let's share that. And we shall begin again. So the following pairs are mixed separately in test tubes. Which pairs would produce a visible chemical change? Silver iodide. Yes, that would. One would. Because that's the test for iodine. Chlorine is more reactive. So yes, that's a visible color change. That's not visible, although it does react. No. So it's 1 and 2 only. That's E. Lap time. Next. Some reactions of metal in the compounds are shown in the diagram. Heated and oxygen. Okay, so which could be the identity of metal M? Okay, so it's M plus. So it's not aluminum, it's not silver, it's not potassium. Okay. So it's a 2 plus. Heated with sulfuric acid. I don't think it's copper because I think the copper is less reactive than the hydrogen. So I'm going to go for C. Next. So 43. Which of the following could be the identity of compound X? Melting point, boiling point. So it's an ionic compound? No. Simple molecular. Oh, it's HCl because in aqueous solution it performs ions, and it's a simple molecular. Cool. Next. 44. Which of the following about losing electrons is correct? Actually, no. Let me go back and check that. No. Yeah, I'm fine. During the electrolysis of molten binary compounds, the ions are attracted to the cathode that lose electrons at that. No, that's not true. If you're attracted to the negative electrode, you gain electrons. Descending group 1 from the atoms lose electrons more easily. Yes, that is true. When a substance is acting as a reducing agent, it is oxidized. Oil is lost. That is true. 2 and 3, G. Next. Which of the following chemical reactions are redox? No, because everything keeps its oxidation state. That is certainly redox because these change to elements. So their oxidation state changes. Here, the Cls don't change, the H doesn't change. Cl3, does the P change? No, I don't think that is. I think it's 3 only, which is D. I'm going to lock that in. Bye-bye. Sorry. Only 2 people are watching? Yeah, fine, whatever. I'm happy to do it for 2. Okay, so is this right? I think this is right. If not, I'm happy to be wrong. Yeah, this is fine. Okay, so here, 3 samples of calcium of different masses were added separately to excess dilute hydrochloric on the volumes of gas. And the volumes of gas released, measured at room temperature, were monitored. 1 sample was powdered calcium, 1 was granules, 1 was a solid piece. Results were shown. So the powdered calcium is going to be the fastest because it is the highest surface area. So this must be the powdered. What is the mass used? Well, we can see that this much volume of hydrogen was released. So calcium and HCl goes to calcium chloride and hydrogen, 2 of those. Volume of hydrogen so N equals 120 over 24,000. Cancels for 2. 1 over 200 is 5 over 1,000. That's the number of moles of hydrogen. So that's the number of moles of calcium. Multiply that by 40. You get 200 times 10 to the minus 3 grams. 0.2 grams is A. Lap time. Sorry, that was a little bit over split. Concentrated aqueous solutions of 3 compounds are electrolyzed with inert electrodes. Constituent elements of which of the following compounds may be collected? Of 3 compounds are electrolyzed with inert electrons. The constituent elements. Aqueous solutions. You could get the copper. Copper would come out. Bromine can come out if it's concentrated enough. Hydrogen chloride. Again, that can come out because you'd also get hydrogen from the water. So hydrogen would definitely come out. It could be chloride. Here, potassium chloride, you can never get out because the water, the hydrogen from the water would come out instead. 1 and 2 only. E next. This had a pH of 1. What's the pH formed when this is added? Okay, so this is the so it's done based on the concentration of the H pluses. So we have 50 times 10 to the minus 3 decimeters cubed times 0.1. Turn that into 5. That's the number of moles of HCl to start with. So calcium hydroxide plus HCl is going to calcium chloride plus 2H2O. So if we have this, so 0.45 decimeters cubed times 0.01, 0.0045 moles of calcium hydroxide. So therefore, it's 0.009 mole of H plus is being taken out. There were 0.005. That can't be right. Moles. Zero, zero. Oh, it can be right. It can be right. So all of the hydrogen reacts, all of the H plus is gone. So it's a pH bigger than 7. Okay, so it's F. Because now there's excess hydroxide. Okay, so here carboxylic acid reacts with propanol in the presence of to form an ester. Relative mass of this. Oh, Jesus. Propanol. So COOCCC HHHH. So then there's going to be an R group we need to work out. So 1, 2, 3, 4 is 48 already locked in, plus 32 plus 1, 2, 3, 4, 5, 6, 7 already locked in. So that makes 55 is 87 locked in. So this R group must have a value of 29. That could be C2H5. So X is propanol, which is 29 plus 12 plus 32. So that is 44, 73, G, done. Next. I'm hardworking. Yes, sir, I am. Element Z is in group 1. A pure sample of element Z consists of 2 isotopes of 85 and 87, relative atomic mass of that. So that means it's a 3-to-1 ratio in 85 to 87. It's in group 1. It reacts with bromine to form an ionic compound. That's not correct. If it's in group 1, it forms Z+, so it should be ZBr. It forms a basic oxide. Yes, it's a metal. Metals form basic oxides. More than 70% have a mass number 85. That is true. 75% of them have a mass number of 85. So it's 2 and 3, which is G. Done. 51. So chromatography paper, test was repeated, but this time the distance traveled was 7.5 instead of 8. The RF values would stay the same though. How far did the most mobile component travel in the second test? Well, it travels the same 7/8 of the way up of the 7.5, which is 15 over 2. Ew. Jesus, what am I going to do with this? So it travels the same 7/8. Well, it's got to be... Wait, hold on a minute. Oh, the distance traveled by the common component was 7.5. Got it. So the common component is this. So it scales up, so it's times 2.5. How far did the most mobile component in Q travel? I am not reading these questions well. So it's 6 times 2.5, which is 15. God damn it! I should skip this. Sorry, times 1.5. So 9, which is C. 52. A typical sample of dry air. Total of gas. One of the gases in the sample contributes... Skip. Second passing this. So I got to come back for 52. I'll circle it. In the real thing, I would flag it. The atomic number of fluorine is 9. Element X forms a fluoride with that. Each has 32 electrons in total. The atomic number is 9, so there's 27 electrons accounted for, so X contributes 5 electrons, which makes sense. It has 2 isotopes. One isotope has the same number of neutrons as protons, so it's 5 and 5, and the other isotope has a number of neutrons 1 greater than the number of protons, so that's a 5 and a 6. The relative abundance of the heavier isotope, so it's 80% 11, it's 20% 10. It's boron. It's 10.8. Done. Here, 1 mole of compound X undergoes complete combustion to produce that much carbon dioxide. Carbon dioxide, C. No, we can do this. So it's carbon dioxide. So it's 12 plus 32 is 44. Decimeters cubed for 1 mole. Let's divide by 4. 38 over 11. I don't like that. Hold on a minute. So 1 mole of X can also undergo an addition reaction with 1 mole of hydrogen to form a saturated compound that has 1 branch. Okay, I'm going to skip this. 54. We're coming back to it. Second pass. It's too sticky. The equation shows the complete combustion of alkane. Cool. 100 centimeters cubes of gaseous alkane requires this much oxygen for complete combustion. Okay, so it's a 1 to 6.5. So it's a 2 to 13 ratio. So alkane, so CnH2n plus 2. I did this before. Okay, so what we know is, let's do the carbons. So from the carbons, there's 2n carbons on the left. No. A is 6.5, full stop the end. We're just doing this. So there's n carbons on the left is equal to B. And from the hydrogens, there are 2n plus 2 on the left, which is 2C. And we know that 13 is equal to 2B plus C. Which means that n plus 1 is equal to C. And n is equal to B. So 1 is equal to B minus C. So C is equal to B minus 1. And that is equal to B minus 1, and B is equal to 14, and C is equal to 13. So 14, 13, and 6. No, that's off. Next. Got it wrong. So 55 I got to come back to. And that's what you do. You just abandon it. So sample of magnesium carbonate reacted completely with that, which is in excess. So 50 times 10 to the minus 3 times 0.1 cancels, makes that 5. That's the number of moles of hydrochloric acid, which is excess. Now Mg calcium carbonate with hydrochloric acid would go to magnesium chloride and water and carbon dioxide. So you need 2 of those. Okay. The remaining hydrochloric acid was titrated with this. So so concentration times volume is 1 times 10 to the minus 3 moles of sodium hydroxide, which is 1-to-1 with the, so the 1 millimole of sodium hydroxide, so 1 millimole of HCl left, which means that 4 millimoles were reacted here, which means that there were 2 millimoles of magnesium carbonate. So mass equals N times MR is 168 milligrams is C. Done. Cool. 57. So 30 times 10 to the minus 3 times 3 is, so that many moles of hydrochloric acid. So ammonia, so NH3 is a base plus HCl. It's going to go to ammonium chloride. So this is 80 times 10 to the minus 3 moles. The initial temperatures of both were that. The maximum temperature was this. So Q equals M, which is the total mass, which is 50. C delta T. That there gives me 1,000 is 4,000 joules. And we know that this thing is the limiting, so that's the number of moles that react. So 4 kilojoules all over 80 times 10 to the minus 3 is that times 10 to the 3, so it's a times 1,000. Cancels, 0.5. So half of 100 is 50, so the answer is F. Okay. 58. oxide of nitrogen can be prepared by the reaction of copper with hot nitric acid. Reaction of copper with hot nitric acid. The other products are copper nitrate and water and something. And an oxide of nitrogen. We know the number of moles of copper. So N equals CV. So 0.16 moles of that. So we know it's a 3:8 ratio. So that becomes 3. So 6 of the nitrogens are there. So N2, that's going to be 4 waters to balance the hydrogens. So 6, 18 oxygens, and 4 oxygens so far accounted for. 24 to play for. So there's N2O2. Or it could be 2 N2Os. Empirical formula, NO, A. I'm just sticking with it because I don't have any other choice, because I've got stuff to get back to. 1 mole of an unsaturated hydrocarbon reacts with exactly 1 mole of bromine. Unsaturated hydrocarbon. Cool. The compound that contains. By mass. Okay. HBr. So it's in a 6:1:8 ratio. So it's 0.5 to 1 to 0.1, which is a 5 to 10 to 1. So it's C5H10Br in simplest form. And I know that if it reacts with 1 mole, there's going to be... Well, let's just... I think it should be fine to do it for this one. So that's going to be 60 plus 10 plus 80 is 150. No, lies. Because that's not possible. Because the 1 mole of an unsaturated hydrocarbon, that should be an alkane. If it's going to swap 1 to 1, that doesn't work. Because that would be C5, it would have been C5H12. No, so we got to double this up. It would have been C5H12, which would have made it C5H11Br if it was 1 to 1. So that's not it. So that's empiricals. Let's double it up. H20Br2. That could work. If 2 is substitute out, that can work. That can work. That can work. Yes. So in fact, it's going to be double the 150, and it's going to be 300E. Lock it in. Done. All right, 60, final one before I go back. Airbags contain that thing is a primary reagent. Potassium nitrate is a secondary reagent. Decomposes according to this thing. The sodium byproduct of the first reaction. Then, so the sodium there then reacts with excess potassium nitrate according to the second equation. Both go to completion. 130 grams of sodium azide. Cool. Total volume of nitrogen gas formed. Let's find out. Okay, so nope, 23 plus 3 lots of that is 54. Nope, it's 40. Nope, blah. Okay, 3 times that is 42. Add the 23. Focus, 65. That's 2 moles. That forms 2 moles of that and 3 moles of that. Let's lock in that 3 moles of nitrogen have just been formed. Then 2 moles of that have gone in. That forms, divide by 5. 0.2 moles So there's 3.2 moles of nitrogen formed. So 3.2 times 24. Well, that is 16 over 5 times 24. Don't like it. How am I going to do this? Well, there's definitely going to be a 0.8. So it's got to be B. Okay. I've got 5 minutes left. Let's go back. I think this was my first one. Total of 25 moles of gas. One of the gases contributes this. Now, 6 times 10 to the 23 is 1 mole. So that is 0.25 moles. Okay. A second gas would alone occupy a volume of this at room temperature and pressure. Well, one of them is 24. So 468 over 24 is 117 over 6 is, divide that by 3. Divide that by 3. So is nearly 20, 19.5 moles of Y. What are the identities of gases X and Y? Dry air. There's a total of 25 moles. Y has to be nitrogen. This is 1%. That looks like it's going to be argon. X has to be argon. Total amount of all the remaining gases. So there's 19.75 accounted for. So it's 7.25 left. I'm going to go with A. I'm going to lock that in. Okay, so this one. Complete combustion to produce that much carbon dioxide. CO2. 44. Oh, absolute filth and lies. Okay, apologies. You see, this is why we come back and do things with fresh eyes. So actually, it was 1 mole is 24 decimeters cubed. Okay, so let's divide by 6. 24 all over 4 is 6. So that's 6 moles. Okay. Complete combustion to produce 6 moles. So that means it's C6H something. 1, 2, 3, 4, 5. No. 1, 2, 3, 4, 5. No. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. 1 mole of X can also undergo an addition reaction with 1 mole of hydrogen to form a saturated compound that has 1 branch. If hydrogens were on there, that would have if hydrogens went there, that would have 1 branch. Hydrogens went there, that would have 2 branches. Hydrogens went there, 1 branch. It undergoes addition polymerization. A section of the addition polymer containing 3 repeating units has an MR value greater than 200. So 3 repeating units has an MR greater than 200 but less than 300. So it's between sort of 70 and 100. So the only difference here is the H versus the F. So 1, 2, 3, 4, 5, 6 gets me up to 72. 1, 2, 3, 4. 1, 2, 3, 4, 5. So 5 and plus 12 gets me to 84. I think it's E. And I've got a minute left on the clock. Final one. I'm not going to get there in time. For the interest of trying to solve it, I will try and solve it after the fact. But in the meantime, let's sort of assume I was roughly right. Let's say it was 7. I'm going to stick with a 0.5, and so I'm going to guess E. So I'm going to lock that in. In the interest of time, I'm going to stop there. Right, what I'm going to do now is actually try and solve this now that the timing is done, and then we'll mark up and see how that went. So I was happy with the multiple passes. I'm glad I didn't burn too much time on this question. I only missed out one, like I only had to guess once. Now, granted, I didn't actually check that I had answered everything, but we're going to find out. So that was a slight flaw in the execution of that exam technique here. But let me try and actually get this done. What went wrong the first time? So it is a 1 to 6.5 ratio for complete combustion. The volumes of both gases were measured at the same temperature and pressure. So therefore, there are 13 oxygens to play for. Oh, well, that was stupid. Of course I got those numbers wrong. And we know that N is equal to B, and we knew that 2N plus 2 is equal to 2C, which means that N plus 1 equals C. So C equals B plus 1. So 13. Oh, that was so stupid. I was so there. So 12. So B is equal to 4. C is equal to 5. 6.5. Oh, it was 15.5. 9 plus 6.5 is 15.5. God damn it. All right, that was totally doable. I just made an execution error the first time. I don't know what it was. So that's a bit annoying. So I was a little slow on time. So as I go, I'm going to first mark it up. And then I'm going to look at my split times and see where I could have done better. So 2022 section 1, let's get the answer key. I'm going to pop it over here with you guys. So starting with 41. Oh, that was section 2. Oops, I got the wrong one. So 2022 section 1 answer key. Starting from question 41. Okay. So it is E good is 42. I got that wrong. So okay. So my chemistry isn't my top science. So I'm not expecting perfection here. So that one I got wrong. It was copper. Oh, of course. That was so stupid of me. Magnesium sulfate solution, you wouldn't get the magnesium back. You would get hydrogen out. So the fact that you get the metal back means that has to have been the copper. I'm sorry about that. That was basic. That was beneath me. I should have got that. It's because I rushed it. I did it in 54 seconds. No, that was poor form. Apologies for that. This was C. This was G. 45 is D, 46 is A, 47 E, 48 F. That paused me for a second. 49, I got wrong as well. 49 is actually H, so I was off by 1 because I forgot to add the hydrogen back. That was really stupid. I forgot to add the hydrogen back for the carboxylic acid. That's so frustrating because my process was entirely correct. 50 was G, 51 C, 52 A, 53 D, 54 E, good. 55 D, I've already discussed why that went wrong. 56 C, 57 F, 58 A, 59 E, boom, I'm proud of that one. and 60B. Nailed it. All right, so 17 out of 20, all of them very annoying technical mistakes. This, I was just sort of running out of time. This, I can't believe I forgot the hydrogen back. That was just not thinking through every step clearly. This one, again, I was just silly thinking about the electrolysis, the fact that magnesium would never come out from a solution. So there are a few mistakes there. It kind of shows you how to go through it. But I think I saved myself by not getting bogged down on questions that I couldn't do. I employed some good skips, which allowed me to like get the questions at the end that I was perfectly capable of getting. Let's look at my split times on that note, just to sort of see if I could have gone better in my working here. So 30 seconds followed by a 54-second mistake, 34 seconds, 46 seconds. So I was building up a good time bank. 40 seconds. This was my first one I went over. No, 6 was the first one I went over. So maybe I could have skipped this one knowing it was going to take me a long time to get to completion on that. Or maybe I could just get faster at my mole calculations. But that took me 2 minutes and 6, which was 30 seconds over budget. This was a nice quick 51-seconder. So again, it's these calculations that seem to be taking me time, because this took about another 2 minutes here. And it's because I was really sitting here thinking about what it meant for, I was like, hang on a minute, there aren't that many moles of H plus to react. And it took me a while to think, oh, well, therefore it's alkali. So I spent some time thinking on that. This one was a 51-second. It would have been so good. Oh, no, hold on. Yeah, so no, this one was 158. Then we had this one was a 45-seconder, which was even better. No, 119 is what I spent on this. This one I spent 45 seconds, which is good. Then we had 1 minute 23 because I was just misreading the question. But notice how I didn't fall down. And once I noticed I was misreading, I went back and like checked it to make sure I was getting it right. And I did get it right, which is good. This one took me a solid 12 seconds. Sorry, this was a 20-second skip. So it was a good quick skip when I realized it wasn't really on the cards right now. This one I got right in 57 seconds. 56-second skip, though. I should have skipped this one quicker. And it's, that was a really stupid mistake. Okay, so that's what cost me some time, is using the wrong formula for working out the number of moles of a gas. That, I was better than that. So it took me 56 seconds to skip, which is not great. Here, it took me 2 minutes, and I burned the time and still got it wrong. So again, not great because I made that execution error. 56. 137 is on the mark for that. 125, again, on the mark. 138, pretty good. 2 minutes, not bad, especially because of how difficult it was to think about it. That was pretty good. This one, 2 minutes again, but we were getting into the part where it was difficult. Then I went back and I did 52. I did this in 1 minute 44 the second time around, so that was good. Then 217 when I came back to this one. So quicker to skip, I think. I like how I got there in the end, that the fluorine, I was like, that would push it too high. This one, that one I just skipped. I have too many lap times and I don't know what my final one was. So I'm not sure these lap times are entirely accurate. I might be a little bit off. But thereabouts. I think it's not a bad run. 17 out of 20 is not bad, especially because I make a few little mistakes. But that kind of goes to show the type of question. There's lots of work out which combinations of things are true. Those are the ones where you have to do them very quickly to build up the time bank for you to burn on the really complicated calculation questions that are going to take up more of your time. And that, broadly speaking, is how to do chemistry for ESAT. So I hope you enjoyed that. I've been on for 2.5 hours now. I'm going to stop because it's Friday and I want to stop. I'm going to have me a weekend. So I'll probably timestamp some stuff. In fact, I've got a little bit of admin. I've got to catch up on my timestamping from the last video as well. As always, feel free to drop in the comments or in the Discord server if you want me to cover something specific for the ESAT. TMUA is largely covered by people smarter than me, so I'm happy to keep doing that. But because ESAT's really more my thing. So I'm going to keep doing what I've been doing, keep churning out the videos. Although I have been super busy, I'm still trying to do it like every single week, churning one out so that you... that was me trying to look at my calendar, and it went horribly wrong. So next week, actually, I'll have to think about what to do for next week. I could do a bit more of the chemistry if you want more of the chemistry. I've solved all of the math and physics ESATs that they have available. I could maybe go through some, again, like alternative resources that you could be using at this point. But in the meantime, if you have any comments, please let me know, and I shall see you guys next week. All right, take care, guys. Bye-bye.